we're going to talk about the limit today. So let us review what we learned in elementary calculus. Recall that. In elementary calculus, when we had a function y equals to f of x, first we deal with the domain of the function, am I right? We say that let d sub f be the domain of the function. Then we are interested in analyzing the limit of the function as the y value as x approaches to some x value on the horizontal line. So here you have your x-axis, here you have your y-axis, and here you have, for example, a, and you have the graph of the function, and suppose this is the graph of your function. So we're just working with a continuous function, and this guy is f of a or L. Okay, let's say that, hey, the limit of the function f of x as x approaches to a from right side must be equal to the limit of the function as x approaches to a from left side, and both of them are equal to each other. It's equal to the y value L. In that case, we say that, hey, the function f has a limit at a. If this is true, it means that the y values are equal to each other and both of them are equal to L. Then we say that, the function has a limit at a, and it is a y value that we call L, for example. However, when it comes to a multivariable function, we are not dealing with exactly y value. The output value that we're interested in is going to be z, all right? So now in multivariable function, in a two-variable function, for example, like z equals to f of x and y, when you're dealing with the limit of the function, remember that the graph of this function is just a surface, a 3D object. So suppose you have your x, y, and z, all right? And then you have your surface, 3D object. This is your S, for example. This is your surface that you have. This is your z equals to f of x and y. When you're dealing with the limits of this function, we are interested in the z value on the z-axis, all right? So remember that the domain belongs to xy plane. Suppose here you have your point x and y in an open circle including this point. X and y approaches to this point. Let's call it A and B instead of just x and y. It's easier to navigate this way. So this point is A and B. We're saying that the function like z equals to f of x and y has a limit at A and B, and we write it this way: the limit of f of x and y as x and y approaches A and B is equal to F. And it must be a unique value, the same as what we did for our function in two-dimensional world. So here the L value that you are looking for is going to be on your, it's a Z value. So this is going to be, for example, your, if it's unique, then you're going to have a limit of the function. But note that it's not the same as like a function in 2 dimensions. You don't have just 2 directions. You are getting closer and closer to this value. This is L. Just move this a little bit here. This is your A and B. And around these points, A and B, you can get closer and closer to this point from many directions, many directions. We have different approaches finding the limit of the function, and also we have some techniques to show that the function doesn't have a limit around near this point A and B. So this is what we're going to discuss. But remember that when it comes to a function in 2 dimensions, you have 2 directions to approach A, from left, from right. If the limit from left, right limit, left limit, they are the same values, then you say that, hey, the function has a limit. But when it comes to 3-dimensional, you don't have 2 directions. You can approach to this point from many paths, many lines, many curves. So if the function has a limit, then it has a Z value. This L is a Z value. It's the third value. You're getting closer and closer to A and B, and your L, if the limit exists, it's just a Z value, Z value. If the limit doesn't exist, it means that there are holes here, or the function doesn't approach to a value that you're looking for, or there is a gap, there is something in between that doesn't let the function approach to that Z value.